to the session on Introduction to SLSA. SLSA is a security framework, and we'll talk about this framework, what it does, what is available around this framework to help you with security of your supply chain. My name is Veer Muchandi. I am an application modernization solution manager. I work for Google Cloud, and I deal with software delivery and serverless areas from this application modernization solutions perspective. So let's, before we get into SLSA, let's look at a few terms that we need to understand before we get into this framework. First, let's understand what is software supply chain. You would have heard of regular supply chain, but what is software supply chain? So this is something that you are already using, but we are just putting some framework around it, right? So think of different kinds of artifacts that are involved as you are building your code and deploying it. So artifacts like, let's say, source code, packages. This could be your jar files or your container images and things like that. And then there are dependencies as well. So some of the packaged things like libraries will become dependencies as you build the code, right? So you have artifacts that are at different stages of your software lifecycle. You have processes like build mechanism, and you have platforms. This dotted line represents the platform. Platform is the place where either your artifacts are stored or the place where your processes would run, right? That makes up your supply chain. So let's think about it. So you have source code, could be the code itself, or it could be a bunch of things that get into a Git repository, like along with a Git commit. So anything of that sort is considered as an artifact. So artifact, where does it get into? It's managed in the source control repository, right? That is a platform. Now, once you have your artifacts in the platform, then you start a process, which is the build process. Build process runs on your CI/CD platform. And then when you are done with your build, you are ending up creating some kind of a distribution package. So example could be a Docker file that is a source getting converted into a container image that gets stored in a container registry. So your container registry is your distribution platform in which your container image gets stored, right? So container image is the artifact, container registry is the distribution platform. And then let's say you are dependent on, while you are building your code, if let's say you are dependent on certain libraries or packages, or even the Docker files, the base Docker file is used to create another your application's container image, let's say, then that Docker file will become a dependency for you, right? So when you put all this together, if you are a developer, you are going through this entire process and you are looking at all these things from the software lifecycle perspective. Some of the packages become dependencies for others, whereas some other packages will get used in your deployed production other environments. Or your customers may also be using the packages that you are distributing, right? So usage is the other process that happens later. So when we say software supply chain, this entire picture coming together is what we are calling as software supply chain. Very easy to understand, we are already using it. Another term, provenance. How many of you have heard of provenance? Provenance is the place of origin or history of something. This is an old term. It is used in many languages. A couple of people are from India here, so I can say that if you heard of the term pravara, it talks about where this person has actually originated from. They tell the entire life history on where their ancestors were born and all that stuff, right? So that same exact term is provenance. Provenance is, it tells you, for in the context of software provenance, it tells you where that software actually originated from. Who is the forefather of this, who is the grandfather of this, everything will come in the software provenance, right? being able to verify the history of your software, where did it come from, how was it built, and what dependencies were used in order to produce it. If you can establish the entire life history of that software, then it is that thing is called software provenance. Why is it important? We'll see that when it comes to the actual security process that we are going to look at. So it enables our consumers to do the basic checking of identifying where the source code has actually come from. If there are vulnerabilities somewhere in those dependencies somewhere, right? If you want to identify where those vulnerabilities have come from, provenance will actually help you. Also, it will help you assess the risk with what software you are running, right? So now that we understood a couple of terms that are required for SLSA, let's get into details on why do we need this framework. Like we have been building software forever. Why do we need this framework now, right? There is supply chain. When it comes to software supply chain, the attacks are increasing significantly. In 2021 itself, compared to 2020, there is a 650% increase in attacks just within the software supply chain. When I say software supply chain, the figure that I showed you earlier, right? The build process, things that are coming into the build, the things that are getting produced through the build. In that entire process, the attacks have increased by 650%. It used to be 430% in 2020, right? That makes it even more important that we need to consider this. Open source vulnerabilities, there is an 84% rise in open source vulnerabilities. And if you are thinking about containers, the Docker Hub itself has 70% of the containers that are on Docker Hub have high or medium security vulnerabilities. You can actually go and look at it directly, right? So that itself is a alarming factor, right? So we need to think about supply chain attacks in this context and why we should be protecting our supply chain. A couple of you are from those companies who are very close to this kind of a threat coming through, right? LexisNexis, Equifax, if anyone is here, yeah. Attacks are not new. So we are looking at attacks are possible as per Ken Thompson, who actually intentionally introduced a piece of code in his Unix platform back in 1984 just to say that, hey, if you are using somebody like me, I can put something in your code so that I can log in into any system that you run. He told this back in 1984, right? Things were not, it didn't go in that direction for quite a long time, but now things are changing, right? 2007, big attack, NotPetya. 2020, this was the big one. Russian attack, while we were all going through the COVID, right? 18,000 networks, including US federal networks, were attacked. And after that, 2021, during the last year, there were so many different kinds of attacks that were big ones, right? These were all the ones that made news. Let's think about how these attacks have impacted the software supply chain. So we have this figure from the first figure that we looked at. How did these attacks impact our supply chain, right? Let's think about it. So first, SolarWinds. This is that Russian attack. They compromised the build platform. Okay. Code cow attack. It attacked many places in the software supply chain, injecting bad code, compromising the build platform, same like the other one, bypassing the CI/CD process, compromising the package manager and signing process so that bad code goes out to the customer to be used. These are different kinds of things that happen in code cow attack. Log4j, this happened in December, just a few months ago. What's here? Vulnerable dependency, right? Log4j is the dependency that all of us use. Most of the Java developers use Log4j. That's a vulnerable dependency. So with the SolarWinds attack, it got so it was so disturbing that even federal government had to issue an executive order saying that we need to be following strict SDLC security policies, and any contractor who works for federal government has to go through that process, right? So this is the context behind why we need a framework like SLSA. I'll explain what SLSA is now. So SLSA, it's pronounced as SLSA, but it is SLSA. The full form of that is Supply Chain Levels for Software Artifacts. Levels in the sense, that means you are trying to measure something, right? And we'll come to that measurements in a few minutes. This is a security framework, it's not a tool. So I'm not saying that, hey, Google will provide you this tool, go and install it and you're done. No, it's a framework. It requires your organization to think through and implement different levels at different points of time so that you can protect more and more, right? So it is ensuring that the amount of security for your software supply chain increases over a period of time. So it is the intent of this framework is to prevent tampering of your artifacts. Your artifact integrity should be increased. That means if you are looking at something, a piece of code to be used, your artifact, your package, your dependency to be used, you are sure that this is a good one to use. It doesn't have vulnerabilities or it doesn't have any defects that can cause problems later, right? It will increase that integrity. Then it also hardens the platforms where you are actually running your build process, your actual usage platforms, right? So if you are storing source code in a source control repository, is that hard enough that nobody else is going and tampering those artifacts? So it is hardening the platform. If you are running build on your build platforms, is that platform hard enough that nobody is going to go and tamper it? Just like that Russian attack that we talked about, right? So it does all that. This SLSA framework covers the hardening of all these aspects. This is not coming from one company. This is a steering group formed by many user organizations like Citibank, like Intel, like Linux Foundation. All kinds of companies are coming together, right? So it's a steering group. It's a cross-organization thing. They all came together and put together this framework based on their experiences. Okay. So SLSA framework, it actually defines the attack vectors into different trust boundaries. And the trust boundaries are source boundary, build boundary, and dependencies. Let's look at what they are. So let's go through where all threats can happen. So think about the first one, where developer writes the code and checks in, right? This is if they have bypassed the code review. Can that happen? How many of you actually do the code reviews before you check in, right? Yeah. So if that is bypassed and people just check in the code without doing the code review, that's one threat, right? That's where things can go wrong. Second part, your source control system could be compromised. So somebody who is not supposed to be pushing code there is actually pushing it. That could be another threat. The third one is your build process gets the source code not from the source control system but from elsewhere. Somebody is actually pushing the code through the build process that is not coming from the source control repository, right? Or some malicious code is being pushed through your build process, bypassing your source control system. That's the third thing. Fourth one, your build platform itself may be tampered, right? The next one, you are taking your build artifact that is actually not coming from your build system. It is coming from somewhere else. Okay? So it gets into your package repository where it is not coming from, it is not built by you. Somebody else has built it elsewhere in a compromised location and they are pushing it. That's the F. Next one, your package repository, that means your container registry, artifact registry like Artifactory or whatever that is, right? That itself could be compromised. The next You think that you are delivering code to your customer, somebody else is actually doing it, right? The actual artifact itself that your customer is using is compromised. Another one, the dependency that you are using is a malicious dependency. Somebody says that it is a good one to use, you are pulling dependencies from some open source, you think that it is the right one. You know, NPM repositories were also compromised, right? The NPM repository is compromised, you are thinking that you are using a particular library of a particular version that is good, but it's not good. So any point in the supply chain can go wrong, and all these threats that can happen at different stages of your supply chain are categorized as source threats, A and B, build threats, C through H, and dependency threats, right? So the framework is just trying to organize things so that we can think logically. Next, oh sorry, do you want to take a photograph? Good. So what does the framework do? Yeah, we identified the threats. We know where the threats are. So what does the framework do? For each kind of threat, it provides a risk mitigation. Mitigation doesn't mean that threat is completely gone. The amount of impact of the threat can be significantly reduced. Makes sense? Right? So we cannot say that, hey, just by implementing all these factors, there is 100% security. That nobody can say. But it will reduce the possibility of having that threat in your organization. So let's look at a couple of them. We cannot go through the entire list today. So let's say somebody is submitting bad code to the source control repository. This is that threat number A. What can you do about it? So one of the possibilities is that we always have a two-person review. One person actually submits the code saying that, hey, this is the code that I want to check in. The other person in a two-person review will actually verify and make sure that this person is doing what he's saying, right? That kind of a thing, two-person review, will reduce the impact of possibility of submitting bad code to the source control repository. This is risk mitigation suggested by the framework. Next, second, compromising the source control platform. What can we do about it, right? Yes, you can do the similar thing like two-person reviews, but first you have to secure your source control platform, right? Anyone in your organization cannot push code into your project, number one. Number two, you can do two-person reviews before you check in the code. But what if someone actually escalates, let's say an administrator is at fault. The source control repository is controlled by an administrator, right? And if the administrator, because they have privileges, if they check in malicious code, they're leaving the company tomorrow, they check in malicious code and go, how do you prevent this, right? First of all, this two-person review is actually going to stop that. But if the administrator escalates the privileges and bypasses that, how do you do that? For that, again, what it suggests is, what the framework suggests is, even if the administrator has to escalate the privileges, that has to go through two-person review. So it's not just the code that you are protecting, you are also protecting the way in which you are managing your platform. Your infrastructure itself, any changes to the infrastructure will have to go through that two-person review process. Example, GitOps process, right? Where somebody submits a PR, in case they have to make any changes, escalate their privileges, let's say, they have to submit a PR, somebody else has to approve it, even if it is an administrator. So now you have at least two-layer of protection for every activity that happens, whether it is an application code change or infrastructure as a code change. Everything has to go through the PR. Does it make sense? Right? Next. What if you are modifying the source code after it passes through the source control? That means you think that the code is actually coming from source control, but it is coming from elsewhere. Your build is actually pulling the source from elsewhere because somebody has compromised your build repository. How do you handle that? That's where provenance comes in. Remember what we talked about, the definition of provenance? Is this code coming from the source? The build process should always check before building on whether this code and the dependencies that I am looking at are coming from the right place. Does the code have history? Do the artifacts that I'm using through the build process have history? Are they coming from the right places that I assume that they are coming from? That needs to be checked, right? So this way, I'm just giving you a few examples. We will not go through the entire rest. Every threat will have risk mitigations that are provided by the SLSA framework. Okay? If the build, let's say the build platform itself is compromised, how do you prevent it? You can have stronger build controls. Nobody just cannot go and log into the build platform and start a build. Number two, the other ways of dealing with it, and SLSA provides these as well. If your builds are ephemeral, that means your build platform is not always running. You are reducing the risk of somebody going and tampering your build platform if it just comes up on time when it needs to run the build and then dies after that. Make sense? If the build itself is ephemeral. Third way, hermetic builds. What does that mean? If the builds can be run in complete network isolation, can we do that? Right? That's the last level. The builds can be made hermetic, repeatable, and completely isolated. Right? These are the kinds of suggestions that for each of the threats, how much security you want at different levels. Based on that, the SLSA framework will give you recommendations on what you can do. Okay? So these are threats and mitigations, and I'll share this presentation with you. You can go through that in detail, or SLSA website also has these threats and mitigations. So how does the supply chain integrity, how is it looked at by the SLSA framework? So remember, we talked about three kinds of threats: build threats, source threats, and dependency threats. Right? We talked about those three kinds of threats. For the three kinds of threats, you have to establish the three kinds of integrity, right? The steps to protect the builds, the steps to protect source, steps to protect dependencies. Now, this SLSA starts with build integrity, then it scales up and adds other integrities. So it starts with build integrity, then it adds source integrity, then it adds dependency integrity. It goes step by step. What do we mean by build integrity? Packages built from things like during the build process, I am actually building based on the packages that are coming from the known sources, as well as that source should not be tampered with. Right? That's the build integrity. I am using the right kind of dependencies that the person who has written the build is saying that, hey, I need to use this dependency, and that dependency is the actual dependency that I'm using, not something else, right? Those kind of things are build integrity. Source integrity, any changes to the source are actually meant to be changes by the person who owns the source code, not somebody else, right? And the change history of everything is available. If something is changed, you can actually verify that it is changed by so-and-so person, so-and-so time, and it was approved by so-and-so person, so-and-so time. There's the source integrity. Dependency integrity, can you apply the SLSA checks even for the dependencies? Let's say if it is third-party libraries coming in, are they also SLSA compliant? Are they declaring that, hey, we are compliant with SLSA at so-and-so level and our dependencies can be trusted? Do they provide that information? Right? That's the dependency integrity. So these are applied depending on the level of SLSA. You start with build integrity and slowly build upon it. You cannot go all over and then completely protect it on day one, right? It takes over a period of time. You'll add security to your supply chain. So let's look at what are those levels. In the first level, look at these green things, and they get added at each level. So the top one represents build, the side one on the left side represents source, and the other one represents dependencies, right? Now you look at each one of them. In SLSA level 1, what does level 1 mean? This is the starting point. You have documented build process. Let's say if you are in an organization, I'm not sure if there is any organization today that doesn't document the build process. So at least you are using, if not anything, you are using an Ant script to do the build. If it is not that as well, if you are just depending on a developer to actually build their code and somehow push it to production, then you are at level 0, which is not even here, right? But if the build process is at least documented and there is infrastructure to say that, hey, the code is coming from so and so place, that is level 1. So this is the place where you have some amount of provenance to prove that, hey, code is located so and so at so and so place, and the build process is documented. In this case, there is no protection against tampering. So people can go and tamper, right? That's level 1. Let's look at level 2. In level 2, we are adding build integrity a little bit. Okay? Here we are adding tamper resistance to the build service. How do we do that? We authenticate provenance. That means if somebody is saying that this source code is coming from so and so place, you are actually signing that. In the sense, let's say your source code is coming from so and so build repository. There is a process that goes and signs that source code. So the build process can verify and say this source code is actually coming from so and so source control repository. Right? If you have such a process established, you are at level 2. It requires version control system. It requires a build service that can actually do this verification and all. Make sense? So you got tampering protection if you are at level 2. And your build service can be trusted now, right? Let's look at level 3. Here we are adding more to build, right? Build integrity. And we also added a little bit more to the source integrity. What are we doing here? You are adding extra resistance to specific kinds of threats. How are we adding more, right? This is where you are actually using third-party auditors to be able to certify that your build mechanism is perfect, right? So somebody else is actually saying that your build mechanism is good. So you may ask me, how is it relevant to me? I mean, I don't care whether third party says yes or no. Yes, you may not care if you are an organization at the fag end. But if there is a company that is providing dependencies to others, you want that company to be accredited by somebody else so that you can use those artifacts as your dependencies, right? So from that perspective, SLSA level 3 is important if you are consuming the artifacts produced by somebody else because they are certified by a third party. Make sense? Right. Now, this is the case where you have guaranteed auditability of your source code and the integrity of provenance is established for your artifacts, right? The level 4 is the highest, and this is where you are adding the dependencies as well, right? It's not 100% there. You can see that it is still black in one layer, right? But the source is fully kind of, you are getting to the highest level of what you can do with source, and with build, you are doing the highest level of what you can do because those are in your hands. Dependencies are still not in your hands. This is the case where you are establishing 2% review process, hermetic builds in the sense you are able to run the build without connecting to network, ephemeral builds, repeatable builds. That means the builds are reproducible. Anytime you want to run the build again with the same set of artifacts, it will get reproduced and it will be the exact same. You are guaranteeing that. And then there are no insider threats as well because you are doing this 2% reviews and all. Make sense? So that is level 4. So ideally you want to get to that level 4. This is the highest amount of confidence and trust you can establish with your supply chain. All right? Next, SLSA levels. Let's look at it from a different point of view. At level 1, you are doing best effort of everything. At level 2, the build is, you are making them credible builds because you are increasing it a notch up, but the source and dependencies are still best effort. At level 3, your build is resilient now because you have added everything possible to the build. For the sources, you have added a notch up. It is credible. Your dependencies are still best effort. At level 4, build and source are resilient. Dependencies are still credible. Make sense? So you are starting with basic security steps, you are adding build integrity, source integrity, and dependencies. Those are 4 different levels of SLSA. Now, the table on the right, it's useful to look at it from what do I need to do in my organization if I want to implement SLSA level 1, level 2, level 3, level 4, right? So look at the table. In SLSA 1, you have scripted builds. If you have scripted builds and you have available provenance, not authenticated, available provenance, then you are at SLSA 1. If you are in SLSA 2, you have source code that is complete version control. So you have established a version control tooling for your source code. You have scripted builds. You have build service that is available, right? You are not just building your code on your desktop. You have a build service that is available. You have provenance. You are adding authenticated provenance. That means somebody is signing it, and provenance is service generated. It's not somebody manually signing it. The signatures happen through a service. So SLSA level 3, again you are adding more retention of the source code history is added. Then from the build perspective, the build is scripted as code. You can actually look at the build in your source control repository. How it is done, it is all scripted down. Okay? And then you have ephemeral environments. That means the build environment comes up and it goes down. We'll talk about examples of those. What does build environment coming up and going down mean? We'll talk about that in a few minutes. I'll show you examples of that. And the build environment is isolated. From the provenance perspective, provenance is non-fallible. So in SLSA 4, everything is checked, right? Moving on. As I said before, SLSA will increase the protection, but it's not a silver bullet. Okay, for example, you can always say that I am at SLSA level 4 with respect to my source code in my organization. We are at SLSA level 4. But you cannot say that the dependencies that you are using from third parties are at level 4. It's not transitive. It's only for you, right? Those kind of limitations are still there. So you cannot establish full graph of dependencies it's not tractable, right? For all the artifacts. It's almost impossible to do that. So we should live with those expectations. So now that you understood what SLSA is all about, let's come to Google's perspective. Let me check the time. We do have time. Google's perspective on what we do. So we have been working for 10 years with this model, and we have come out with the same tooling for now our customers to use. What we do with this is we do a policy-based mechanism, establish policies so that nothing can come out of that policy as an exception, number one. So it is policy and trust-based model. And we create these attestations at different stages of your SDLC. So for example, in the develop stage, you have attestations, that means somebody is signing it. At the supply stage, we are signing it. So anything coming from outside, it is signed by somebody. And if you are building, after the build, it is signed. So any artifact, you are establishing the trust by using attestations, right? Signing. Again, when I say signing, it is done by software automatically. It's all automated. Next thing is, when you deploy your code into any runtime environment, you want to verify the trust by checking the signatures, right? Just like how when you talk over SSL with HTTPS, you are checking the signature of the server or the client. In the same way, when you are using your built artifacts and you deploy it into your environments, you are verifying that it is coming from the right place and it is signed and it has been built in the correct way, it is coming from the right sources, is something that you are verifying by verifying the signatures. The third, once it starts running, you still need to maintain trust. So there is a continuous check that needs to happen to identify if there are any new vulnerabilities that will come up as the code is running in production, right? So you need to do all of them. Now, SLSA stops at verified trust. It doesn't talk about continuous monitoring in production. But this is Google's perspective. We also need to do that, right? Next, we do provide tooling that cuts across all the entire life cycle. Let's think about it. Source control. We do provide source control repositories that will enable attestations, right? And it is protected, it is private. Next, cloud build. How many of you have heard of Tecton? Are you using Tecton? Not using it, yeah. Tecton has its origins from cloud build. So remember I was talking about ephemeral builds, ephemeral in the sense they come up, they need to, whenever they need to run, they'll run, after that they'll go down, right? That's exactly, it is serverless mechanism. So your build servers are not always running. Your build is written as code. I'll show you how that looks like. And when it needs to run, it will come up, you will run the build, and after that it goes down. So think about when you have ephemeral builds, the attack surface is significantly reduced. The build server is actually running something only when you are running the build. After the build is complete, there is nothing else. So compromise is very limited, right, in such a case. So that's what we provide. So cloud build is that mechanism where you can run your builds in an ephemeral way, repeatable way on a protected infrastructure. Third, as part of your cloud builds, you can run scanning of the artifacts that you produce. So for example, if you create a container image, you can run a scanner against that container image that is produced right after it is produced, even before it is checked into the source control repository. So before Docker push, you can scan your container right then and there through the build process. And if you are happy, if there are no vulnerabilities, then you can push it. That's one way of doing it, right? Next, artifact registry is like your Docker Hub. How many of you have heard of GCR, the container registry? You have used GCR, right? So artifact registry is the next version of GCR. So basically, in artifact registry, as soon as you push your your container image, it gets scanned immediately. You can just enable the scanner and it gets scanned immediately, right? And if there are any vulnerabilities, those will be identified. And the report of those automatic scans are stored as image metadata so that you can decide on what to do with that. So for example, maybe there are some medium or small vulnerabilities, and maybe you are okay with those vulnerabilities in your dev environment, but you don't want to push them into your production, let's say. So you can make those decisions based on the data stored in your image metadata for each image. Then cloud deploy. Cloud build is your CI mechanism. Cloud deploy is your CD mechanism. So cloud deploy allows you to actually do your transition of your code from dev to QA, QA to staging to prod kind of thing. Okay. So again, this is all, cloud deploy is all scripted and it is ephemeral. It's not always running. It comes up when it needs to run, it is serverless, and it goes down after your job is done. Then you have audit logs. Binary authorization. This is a mechanism where you can actually protect your runtimes, like let's say GKE, Kubernetes engine, or serverless environment like Cloud Run with binary authorization. What it does is it adds policies to your runtimes so that unless it is signed by the authorities that you want it to verify, the application will not get deployed into that environment. Let's think about it. So let's say you are deploying into QA. You want to check the attestation that this source is actually coming from so-and-so source control repository, right? If you want to deploy into QA, in addition to the first attestation, we also want to check that the development environment has actually signed off. Only then I want to deploy it into QA. If you are deploying into staging, you want to add another attestation that it is coming from the right source, it is built through the right build process, it has been verified by development, and there is also a QA attestation. And in production, you want everything, all 4 different kinds of attestations, right? So that can be enabled by just configuring those using binary authorization. You can say with binary authorization, just by one simple configuration in 4 lines that, hey, I want these particular attestations to be available before the code gets, or before this application runs in production environment. And then it will automatically enforce it. It will not allow anything else to be running in your production environment. That means even if there is tampering done elsewhere, it will not get into your production because the attestations, the check with binary authorizations is preventing it. Make sense? All right. So mapping these tools back to our SLSA. So on the source control, what all it takes care of from SLSA requirements perspective, your version controlling is taken care of, verified history is taken care of, retention of the history indefinitely, that is taken care of, 2% reviews can be enforced to the source control. Same way with the builds, scripted builds, you can, the cloud build, the one that we talked about, right? It's all scripted builds only, right? You are writing the build as your source code, you are pushing that build mechanism into a source control repository, you are running it through the PR process in case it needs to change it. Build service is offered, build is available as code, and it is ephemeral as I spoke to you about it, right? Provenance, availability of provenance, authentication of the provenance because you have attestations, it is service generated, non-falsifiable, and content requirements are met. In addition to all this, secure baseline, access control, and super user configuration are all handled by the common platform thing that is provided by Google Cloud. What we also offer is a solution. Now, if any of you are interested in trying it on hands-on with you as well as your team, send me a message. I'll share the email with you. We can organize a free session, a free workshop for you on how to implement supply chain security in your organization. Okay. Basically, we have 5-stage mechanism of implementing secure software supply chain. It starts with how to secure the baseline, step-by-step process. How to secure your source code, your infrastructure, your baseline, right? After that, it goes to how to secure your source code, how to check that your artifacts are good before deploying, what do you need to check after the artifacts are deployed, and what do you need to ensure for promoting the artifacts. So this is, the last part is CD, the part where you are at artifacts before deploy and deployed artifacts, that's the CI process. So at every stage in your software supply chain, what all factors need to be taken care of and what all do you need to implement in terms of supply chain security is something that we have built together as a hands-on workshop, right? It is not dependent on Google tools. You can apply it with any tools of your choice, but our tools are like completely stitched together. So you don't need to go here and there, like everything works seamlessly, right? But if you want to run this workshop, you can just learn the concepts through that workshop. Now there is also a publication. Take a photograph of this, go to this link and read about shift left security. It has complete details on how to do it in these 5 different stages. Okay. All right. Let's look at a quick demo. I cannot show everything that can be done, but I'll just show you a small piece of this the scanning mechanism. Okay. Escape. All right. So I have an application, and this application is already, I have set up a pipeline for this application already. What I'm going to do is show you that there is a Docker file in this app. There are 2 different types of Docker files. One is a bad one, which has some vulnerabilities, and there is one that is good, right? We'll first use a bad Docker file, and we will push it and see what happens. So I'm going to okay, I copied the bad Docker file. And I'm committing my changes to a source control repo. Right? Now, as soon as I do this, find the so there is a build that got started in that cloud build. This what you are seeing is Google Cloud Console, and this is the Google Cloud build interface, and the build process has started. Let's click on this to see what's happening here. The build itself includes 5 different steps. This is all based on code. The build is actually coded. The first part, step 0, is building a container. The second step is running some unit tests. The third step is pushing the source code into artifact registry, that is the container registry. The fourth one is vulnerability check and signing. And the fifth one is release to CD process, cloud deploy process. As we were talking, the build process has run. So what happened here? The build container, let's click on this and look at the right side for logs. The build was successfully done and it created a container image, right? This US central one docker.package.dev. This is the artifact registry, and it created an image with this tag. Then the unit tests were successfully ran 2 tests and it was successful. Third, it pushed that image into the artifact registry. I could have actually included a scan step before pushing and prevented it from pushing, but actually I wanted to show you something. That's why I pushed it even before checking. And then the next step is vulnerability signing. Here I'm using Critis Signer to do the attestations that we discussed about. And this attestations thing is actually running a scan to check whether I should sign it or not. And I'll show you what it means. Here it says this step has failed because it found 2 different violations in this image that it is scanning, and it has severity high exceeding the maximum unfixable severity of medium. So let me show you what it does. So I have set the container analysis policy. When the signer signs, it actually checks image vulnerability requirements here. Fixable severity, I set it as medium. You can lower it, then it will go through, right? And unfixable severity, medium. So because I set it as medium and there were high vulnerabilities, as the logs are saying, with that image, it actually did not sign. The signature process has failed. So the build stopped there itself, right? So you can actually configure on what kind of severity you want to allow for your images into a particular environment if you want to sign it and allow it. Make sense? So you can fine tune it. As an administrator, you can decide what is allowed in which environment for you by using this approach. And it's all scripted, it's all code, right? If someone is making changes to this to allow a vulnerable image to go through, it has to go through a 2-person approval process to make that change through a PR process. Make sense? Now, we know that this build has failed, right? Let's do this. This time, I'll use the good Docker file. This time I'm pushing a good Docker file, and here, if we go back and check, it would have started a new build, the latest one, and the build starts running again. So again, it goes through the same exact process. This time the vulnerability signing should succeed, and after that it goes to the next step of releasing it to cloud deploy. Let's look at, while this is happening, let's look at cloud deploy. So remember, in that figure I showed you that the build happens first from the source control. It triggers a cloud build, which is the CI process, which is what is running right now, and after that it hands over to the cloud deploy so that it moves from one environment to another. So what cloud deploy does is, this is a pictorial representation of moving that code from dev to test, test to staging, staging to prod. If you want, you can also have manual intervention here. So remember the two-step verification process. If you want another person to approve before moving the code to production, you can always have an extra step for somebody else to approve the move to production, as an example, right? You can also have this anywhere you want. I'm just showing one example of before production, it has to be approved by two different people, right? So this entire process of cloud deploy is all scripted. Basically, this is all code. You deploy some code, and the code looks like this. The CI code looks like this. You are saying, hey, I'm going to allow so-and-so criticality. The image that is built should be named so-and-so, right? And then I'm running different steps in my build process. Step number 1 is build the container, and I'm running Docker build using the Docker file. Step number 2 is push that container, Docker push, you can see that, right? The step number 3 is vulnerability scan and signing. Step number 4 is initiate the cloud deploy process. Make sense? So entire CI process is coded, as well as once it completes the job, there is nothing running. Your CI system is not there after it completes the job. It runs on cloud. Once the job is complete, it goes down. There is nothing running there. So the tampering is not possible, right? After it goes down. Let's look at the build. So this time the build is successful. So it got released to the cloud deploy. Let's go back to cloud deploy and see. So I'll refresh this. So now I can promote this from test to QA and QA to production. So I can say promote. Actually, before promoting, we can also check what has changed from the previous build. Let's look at it here. So basically, this will deploy it into the test environment, and after that, it will be ready for staging. And let's look at the promote here. So you see that if there are any differences in manifest, you can see here. What is the difference between the previous Kubernetes service and the current Kubernetes service? It will actually show you the previous release and the current release. What is the difference between the previous Kubernetes deployment and the current Kubernetes deployment? So the person who is actually promoting can actually verify what they are signing off to be deployed into the next environment. The tool shows everything up front. Okay. So let's go back to our presentation. You saw how this works, right? So basically everything is fully integrated. After the cloud build is done, it hands over to the deployment process, and the deployment process is all like, you can click and move it all the way to the production. See, the test deployment is now complete, and it is going to staging, and it's just complete just now, right? So let's go back. We are coming to the end of it. So in case you want to try it, there are a couple of things you can do. One, you want to try it yourself, use the $300 credit that is available on Google Cloud, right? Use the developer account. Second, there is a secure CI/CD blueprint that we have created. It's available for anyone, free to use. These are a bunch of Terraform scripts that you can use to set up your own secure CI/CD platform, right? Take a photograph of this. This is a Git repo. Anyone can take it and use it. This is new. We just built it and released it a month ago, I think. If you need any help with this, get in touch with us and then we can help you out. The last, if you want to learn the S3C concepts, the secure software supply chain concepts, and you want to do it for a bigger group in your enterprise, like a bunch of developers coming together, just send me an email at this, send us an email at this email address that you see at the bottom. We can organize that session for you. Okay? So that's it I had. If you want to take a photograph, you can. Thank you so much for attending. Mm-hmm. Yeah. So basically, you remember the metadata thing that I showed you? We capture the image metadata here, right? So the image metadata will have complete information of how this image was built, what all is included in that image. Now, we get vulnerability reports, the CVEs from different organizations at different points of time, right? So we know what is running in production based on the image metadata. Anytime we get a new vulnerability, it goes back and checks to see if any of the applications running in production are affected based on this new vulnerability that is just discovered. And based on that, it will tell you that, hey, but for this particular application, we have a new vulnerability discovered. So for example, Log4j. When that happened in December, I had some applications running on my Kubernetes environment, and I was getting automatic notifications saying, this application is potentially impacted by Log4j. Go and upgrade your application to use this newer version of Log4j and things like that. You can configure it, whether you want it every day or every hour or whatever that is.